Okay, welcome back, oceanography students. Hope you guys all did well on your exam. Today we're going to be moving on to seawater chemistry. So you can find the slides for this lecture here, week 5 slides. There will be a homework assignment in the quizzes section that will cover this lecture. That's due Sunday before midnight. Okay, so let's get started here. Seawater chemistry. So you guys have probably heard all the time, over and over again, water is the ingredient for life, right? Without water, Earth wouldn't be such a unique biological hotspot. And it's not a coincidence, right? Water has a lot of very unique chemical molecular properties that allow it to be the versatile substance that it is. So today we're going to do a little bit of chemistry, right? So the first part of this semester we've looked at the geology, right? How did the oceans form? What does the ocean floor look like, right? How does the ocean have volcanoes and the types of things? So now we're going to look more closely at the chemistry of water, the H2O molecule itself, and we'll discuss these sort of 5 magical or unique properties of water. So we're going to zoom in today. We're going to look at water on a microscopic scale. And in order to do that, we need to have, a somewhat basic understanding of a microscopic scale. So today we're going to be talking a lot about atomic bonds, especially the atomic bonds between water molecules. So just a little bit of review, right? Here we have an atom, right? And in the center of the atom, we have something called the nucleus. The nucleus contains protons and neutrons. Protons have a net positive electrical charge, whereas neutrons, the red dots, have no electrical charge, right? They're neutral. Surrounding the nucleus, you can see we have electrons. Electrons have a net negative electrical charge. So this is important when we look at the attraction between water molecules, right? We have to understand electromagnetism. So you guys have probably heard this before, right? Opposites attract. But different electrical charges, right, exert an attractive force on each other. The same types of electrical charges, right, positive and positive or negative and negative, those will repel each other. So one important factor of this is, what is the charge, right? How strong is the charge? And the second important thing to know is, what's the distance between those two charges? So here you can see these two charges are very close together. And when we look at the reason why, it's because in electromagnetism, the smaller the distance between the two charges, the greater the electrical attraction or repulsion will be. So if this little plus guy was all the way over here on this end of the screen, it would be less of attraction than for when he's sitting right here. The closer two charges are together, the stronger that attraction will be. Okay, so when we look at the atom, right, we have to think, okay, well, what's the forces involved in keeping this structure together? So electrons are negatively charged, protons are positively charged. So the electrons are attracted to the nucleus because the nucleus has a net positive charge. But what keeps the protons and neutrons together? Because neutrons have no electrical charge. So what keeps them here, cozied up with the protons? And for that, we can look at the 4 forces of nature, right? So gravity is one we talked a lot about with plate tectonics, right? The attraction between masses. And we just discussed electromagnetism, right? The attraction between positive and negative, or repulsion between similar charges. But there's also two other forces in nature that you might have or might not have heard about before: the strong force and the weak force. And these are both forces that work at the subatomic level, not something that you really notice in your everyday life. And what holds the protons and neutrons together is the strong force. Right? This is what holds the protons and neutrons together in the nucleus. It's just one of those forces in nature. Okay, so now that we have an understanding of the atom, we can apply that to the periodic table of elements. So shown here are all the known elements that we have. And, we'll probably discover more in the future. But how they are grouped is according to something called their atomic number. So let's look at nitrogen here. We've got the N, it's a symbol for nitrogen. And then we have these two numbers. Up in the top left, we have the atomic number. And then at the bottom, we have something called the atomic weight. The atomic number is the number of protons in the nucleus for this particular element. So nitrogen has 7 protons. The atomic weight is the combination of both protons and neutrons. So here we can see that nitrogen has 7 protons. 14 minus 7 is 7. So that means nitrogen also has 7 neutrons. Let's look at another example. Here's carbon. So here's the 6 up here telling you that carbon has 6 protons. And at the bottom you can see the 12. Right? 12 minus 6 is 6. So carbon has 6 neutrons. And you can see that displayed here, right, in the atomic map. Here's the 6 protons and 6 neutrons in the center in the nucleus here. And you have the electrons orbiting about the nucleus. Oops. So let's look at now the 2 elements that are going to be most important for today's discussion. So water's chemical formula is H2O. So what that means is for every 2 hydrogen, you have 1 oxygen bonded. So let's look in depth at these 2. Hydrogen, look, it has the number 1. So it has 1 proton, 1 electron. Whereas oxygen has 8 protons and 8 electrons. So when we look at their atomic mass, right, we can see oxygen is a lot bigger in atomic mass, right? 1 versus 16. And this is important, right? So because oxygen is so much more, it has such a larger amount of electrons, that means it's more electronegative than hydrogen. So we'll come back to this. What happens when atoms meet? Right? So when 2 atoms meet, they form a bond. Now there's different types of bonds, and we'll go over that in a minute. And when they bond together, they're called molecule. 3 different types of bonds we'll discuss today. The first are covalent bonds. Covalent bonds is when 2 atoms share electrons, right? So you can see that here. Electrons aren't transferred, right? They're simply shared between the 2. So that's called a covalent bond. A second type of bond is known as an ionic bond. And this is where you will have 1 atom will gain an electron and 1 will lose an electron, right? So gaining an electron gives an atom a negative electrical charge, right? Because remember, electrons are negative. So if we add a negative electron, then we will get a net electrical negative charge. If we lose that negative electrical charge, right, it will give the atom a resulting positive charge. These charged atoms, right, whether that be positive or negative, these are called ions. So ions are atoms that have a charge. So covalent bonds is we're sharing electrons, right? We're nice, we're friends. Ionic bond is one atom steals or takes away the electron from another, and that results in them both having a positive and negative charge. The third type that we'll come back to, is something called hydrogen bonds. And these are a lot less common, and this is what gives water almost all of its special properties, are these hydrogen bonds. Okay, so we'll go through today and look at, I have here the 6 magical properties of water. Now, obviously, you guys know it's not really magical, right? But it can seem like that because of all these really interesting ways that water allows for life to propagate. So we'll go through each of these and discuss how that's related to the chemistry and looking back at the water molecule. This is a picture of the H2O water molecule. So 2H, right, 1O, H2O. The hydrogen atoms form a covalent bond with the oxygen atom. All right, so these bonds here between the hydrogen and oxygen are covalent. And we can sort of remember the structure by remembering that this is oftentimes called the Mickey Mouse molecule, right? Because it kind of looks like Mickey here, right? There's the nose, there's the Mickey ears. So this is the general picture of the water molecule here. Okay, so now let's go into a little bit more depth with that picture. So we flipped Mickey upside down, right? Before his ears were up. Now Mickey's ears are down here. So just so you have a reference for that. So remember we talked about oxygen having more electrons, right? Oxygen has 8 electrons. Hydrogen only has 1. And so because of that, oxygen has a much stronger electrical charge, right? It's much more electronegative than hydrogen, right? And it's so much more electronegative that it actually ends up pulling hydrogen's own electron away from it, right? And it keeps it closer to itself, right? So as a result, right, this is what makes the water molecule so unique that other molecules don't have, is because of this strong difference, you get a partial negative side of the water molecule and a partial positively charged side of the water molecule, right? So because oxygen is pulling these electrons away from hydrogen, right? It's not stealing them. It's not taking them completely. It's just pulling them towards it, right? Very strongly. And remember, if we gain an electron, we get a negative charge. So here we're not gaining it, but we are moving it closer to the oxygen atom. So that gives this end, right, Mickey's chin, right, if this is Mickey, a partial negative charge. And then the ears, the Mickey's ears, right, these poor hydrogens had their electron pulled away from them. They're so sad. And that gives them a partial positive charge. So this polarity, right, the fact that water molecules have 2 poles, a positive side and a negative side, is what makes them so unique and what leads to all of the special properties in water. Okay, so now let's apply that. Here we have one water molecule, one Mickey Mouse head. So these hydrogens are bonded to the oxygen by a covalent or a sharing bond. But what about the bonds between water molecules? Right, so here you can see we've got 4 other water molecules. And when these special properties come into play is when we start to look at the interactions between different water molecules, right? That's where all the properties emerge. And this is through something called hydrogen bonds. So this is a special type of bond that is solely a result of the fact that, remember, a water molecule has a positive end over here by the ears and a negative end over here by the oxygen. What that means is that when this water molecule comes into contact with another water molecule, the positive end of this water molecule, right, the ears of this one, will be attracted to the negative end of another water molecule. Right? So that bond is called a hydrogen bond. It's a result of the attraction between water molecules. And that's what leads to all of water's special properties. Okay, so now let's look at some of these properties. What does this hydrogen bonding lead to that we would see on a macroscopic scale in nature and in our oceans? The first are three properties known as cohesion, adhesion, and surface tension. Cohesion is the ability of a substance to stick to itself, right? It clings to itself. And this is because the hydrogen bonds between the water molecules, remember, they're holding that water together. And this is what makes water droplets possible, right? If you have a little eyedropper of water and you dropped a little droplet on the desk, it would bead up, right? But if you did that with, say, oil, right, the oil would spread out, right? So that's called cohesion. H2O sticks to other H2O molecules via hydrogen bonds. Adhesion, on the other hand, is similar, but it has to do with the clinging of one substance to another, right? So water likes to stick to stuff, right? We all know that. Water makes us wet, right? So adhesion is when water sticks to non-water molecules, also via hydrogen bonding. So that comes into play when we look at things like trees and the transpiration of water, right? Because water has the ability to stick to itself, and it also has the ability to stick to other surfaces, this gives rise to transpiration. Water can move up the tubes in plants, right? And this allows the tree to sustain itself, right? And without those properties of water, without cohesion and adhesion, you wouldn't see that. We also get something called surface tension, which is a result of cohesion. And this is the tendency for water to form a thin layer, right? And you may notice this if you ever go out to, a lake or you're at the beach and you throw a stone into the water, it has to break that surface, right? So surface tension is a measure of that. So a lot of organisms will utilize this property of water, this surface tension, in their own ecological niche. So you may have seen like a water stick insect, or maybe even there's this special lizard. It's called the Jesus Christ lizard.
This is not juggling.
So
this is called misdirection.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
The next property that we will discuss is the fact that water is something called a low density solid. Right? So you may know this from the fact that ice is less dense than water. Water is the only type of matter which becomes less dense when it's in a solid form. All other types of matter, right? Solid is the densest, liquid is the next densest, and then gas is the least dense. But something strange happens to water as it approaches the freezing point. Right? It becomes most dense at 4 degrees Celsius, but then when it freezes to solid ice at 0 degrees Celsius, once it becomes a solid, it's actually less dense. Right? So ice floats just like it would, in your soda, or we have our polar ice caps, right, which float on top of our oceans. And you can see that reflected here in the molecular structure, right? So when water is in a liquid state, the water molecules have less space between each other. But when water is in a solid state, the water molecules have more space between each other. And density is a function of how many atoms are packed into how big is space. You can kind of think about the analogy of say you're going to a party, and at the beginning of the party there's 2 people in the whole house. So you'd say it's not very densely packed, a party. But then maybe 2 hours in, you've got like 30 people in that same house. You'd say it's more densely packed. There's more people in the same amount of area than before. So this property of water, the fact that ice floats, means that life can survive year-round, right? So that means every winter, lakes don't entirely freeze over. Instead, you get a thin layer of ice that freezes at the top, and then life below that ice can survive through the winter, right? In the liquid, it's also protected from, the harsh winds and weather of winter. So without that property, right, without water being a low density solid, it's very unlikely that life could have evolved. The third property of water that we'll discuss is something called a high specific heat capacity. So what heat capacity is it's the amount of heat energy needed to increase the temperature of something by 1 degree Celsius. Right? How much heat do I have to apply to warm something up? Water has a very high specific heat capacity. And what that means is that water can absorb a lot of heat, right, without increasing its baseline temperature. So there's many reasons why this is good for life, right? And one of those reasons is, if you think about organisms like people, we're something like 70% water. And if water didn't have a high specific heat capacity, every time it would get hot out, our blood would boil away, right? But because we're mostly water, our bodies resist those temperature changes. It keeps us at a very nice stable level because it takes a lot of heat energy to warm water up. You can also think about this, we'll talk about this when we look at climate and the Earth's atmosphere. But large bodies of water can have a moderating effect on nearby land temperature. So because the oceans are water, the oceans can take in a lot of heat from the sun and not heat up. And you may have noticed this before. If you're going to the beach on a hot day, you jump into the ocean, it's not as hot as the air. It's so much colder because it takes so much more heat to heat up the water than the air. This is why temperatures are always so much more moderate on the coast, right? Over in, Santa Monica, the daily highs and the daily lows are very close together. It doesn't get really hot on the coast. Whereas if inland, right, out in the desert, the highs are very high and the lows are very low. It gets really hot during the day, like in Death Valley, and really cold at night because there's no water there to moderate, right? To have that sort of stabilizing effect on the landscape. Okay, so let's have a look. There's this experiment, this balloon experiment that demonstrates
the great enemy of writing
high heat capacity.
Isn't
the balloon experiment. The next property that we'll discuss is the high heat of vaporization and fusion. So you guessed it, water has both a high heat of vaporization and a high heat of fusion. So the heat of vaporization, that's the amount of heat that a liquid has to absorb before it can be converted into a gas. The heat of fusion, it goes the opposite way. It's the amount of heat a solid must absorb to be converted to a liquid. So how is this relevant? Well, if we go back to biology, right? We look at the relevance of sweat. When it's a really hot day, your body cools itself down by sweating. So why is it doing this? Right? Your body is essentially allowing a thin coating of water to cover your skin, right? And when that water evaporates away, right, it takes all of that heat energy with it out of your body. So without sweat, right, your body would hold on to all of that heat energy. So this is one mechanism by which organisms like humans utilize the high heat of vaporization to provide a homeostasis. The fifth unique property of water is a very powerful solvent, right? So this is solubility. And this is due to, remember, its polarity, the fact that water molecules have a partial positive and partial negative charge. And because of that, right, these water molecules will form something called a hydration shell. And many molecules are able to dissolve in water if they have ionic and polar regions on the surface. Organic matter can either be hydrophilic, meaning it's attracted to water, or hydrophobic, meaning it repels water, right? So one example of a hydrophobic substance would be oil, right? If you pour oil and water into a glass, the oil will sit on top of the water, right, in a thin layer. They won't mix together, right? Whereas hydrophilic substances, it's the opposite. They will interact with the water. So if we look here, if we put a salt cube in a beaker of water, salt is made of sodium chloride, sodium being Na, chloride being Cl. And when you put this hydrophilic substance in water, right, the water, it basically attacks the sodium chloride, and the negative oxygen regions of the water molecules will be attracted to the positive sodium ions, whereas the positive hydrogen regions of water molecules will be attracted to the negative chloride ions. So solubility, water is a powerful solvent, and it's another reason why life is so advanced, right, on this planet, is because of water's ability to be a powerful and versatile solvent due to its polarity. Okay, so that's the end of my lecture, but there's a video that you also need to watch. It's 12 minutes that I will post in addition to this lecture, that you will need to do your post-lecture quiz / homework assignment that's due on Sunday. Okay, thanks for tuning in again, you guys. Stay safe out there.